So, hello to everyone who's watching on YouTube. So, since no one has joined the session in person yet, so I'll be waiting for like 5-6 minutes so that a few people can join the session in person. So, if no one joins, I'll just start discussing the problem statement nonetheless. So, yeah, I guess I'll get started in like 5 minutes. Yeah. Okay, so I guess since no one has joined the session in person yet, so we can get started nonetheless. So first of all, just to introduce myself. So hello everyone, I'm Lakshya Saggi, the TA for NPTEL Competitive Programming course, the problem solving TA for the Tuesday 6 to 8 p.m. sessions. So this will be our ninth session, I believe, and in this session, we'll be discussing problems related to max flow and min cut duality. So last week we discussed problems related to maximum flows. So today we'll be discussing problems related to the duality between the minimum cuts and the maximum flows. So yeah, so I have a bunch of problems created for this. So hopefully these problems will help you guys get through this week's assignment. So yeah, so maybe I can share the problems now. So let me just share my screen, guys. Okay, so I hope my screen is visible because there is no one to give inputs on. There is no one in person present to give inputs on whether the screen is visible or not. So I'll just be assuming that everyone can see. So yeah, so I guess we can get started with the problem directly. So once again, I'll be assuming that so like every week, I'll be assuming that you guys have gone through this week's lecture videos first and you're attending you're watching this session only after that because I'll be assuming the things which were discussed in this week's lectures, like I will assume that you guys know what is maximum in cut duality or what are actually cuts in a network and so on. So yeah, so the thing that so I'll be assuming that you guys already know what these things are and we'll just be discussing problems related to that. So yeah. So I guess we can get started then. So first problem says that which of the following is true about a minimum cut in a network? So it's more of a definition based problem. So the problem asks us which of the following statements is true about minimum cut in a network. And the options are so the two statements which claim what a minimum cut is are so statement one says that it is the cut that separates source and sink with the minimum number of edges. And second statement says that it is the cut that separates the source and the sink with the minimum sum of capacities of edges. So note that statement one says that so a cut we already know that it separates source and sink in the graph. It's a set of edges which when deleted separates out source and the sinks in the graph. So now the statement one says that this cut has minimum number of edges, and statement 2 says that this cut has actually minimum sum of capacities of the edges. So and the options are just like saying only statement 1 is correct, statement 2 is correct, or both are correct or both are incorrect. So I'll so you guys can pause the video and think of this answer yourself, and just be writing down the correct answer because this is more of a statement definition based answer. So the correct answer is option A. So option B, sorry, which claims that it is the cut that separates the source and sink with minimum sum of capacities of the edges. So note that the size of a cut is defined as the sum of capacities of the edges. So minimum cut is the cut which separates source and sink with minimum sum of capacities, not number of edges. So it is clear from definition of minimum cuts. So yeah. So one thing from the definition of minimum cuts as discussed in the lectures. So one thing to note is that suppose you don't have to find out the cut that separates source and the sink with minimum sum of capacities. This is what you call the min cut. But suppose you had to find this cut. Suppose you had to find a cut in a graph which separates source and sink with minimum number of edges. Suppose you are given a graph, you are given some edges and so on. So you already know how to find out a min cut. So you can already find out a min cut. But suppose you have to find out a cut that separates source and the sink with the minimum number of edges. So you don't need minimum sum of capacities, but rather minimum sum of edges. So how can we compute this using minimum cuts? So this is also an interesting problem, and you can just see that what we can do actually here is that put the capacity on every edge as 1. Suppose every edge has a capacity of 1, then what happens is that the sum of capacities of edges just becomes equal to the number of edges. So the cut with the minimum sum of capacities will be the cut with minimum number of edges also. So note that if all the edge capacities are 1, then these two, statement 1 and statement 2, both are the same, because capacity is equal to the number of edges if the capacities of all edges are 1. So this is just a note which I can add, so that so just to increase our knowledge. So if all the edges of the graph have capacity 1, have a capacity of 1, then the minimum cut is also the cut with the minimum number of edges. So it also has minimum number of edges. This is because if capacities are 1, then the sum of capacities becomes equal to the number of edges. So I don't think this is very complex. So yeah. Because so yeah, I don't think this is too hard to follow, because like if all things are 1, then sum of 1 is just equal to the size of the set. So yeah. So this is just a note, but the correct answer is option B. So maybe I can just underline this so that it's clear to everyone that what the correct answer is. So yeah. So then we can, I guess, move on to the second question. So second question says that so it's a bit of an interesting question, because I just wanted to test out the concepts for everyone for the minimum cuts and so on. So in a directed graph, the size of ST minimum cut is equal to size of TS minimum cut. True or false? So what do I mean by ST minimum cut and TS minimum cut? So suppose S is the source and T is the sink, then we denote it as ST minimum cut. So similarly, TS minimum cut will mean that T is the source. So T and S are just vertices in a graph. So if S is taken as source and T is taken as sink, then we will obtain one minimum cut. And suppose we take T as the source and S as the sink, then we'll obtain another minimum cut. So are the sizes of ST minimum cut and TS minimum cuts equal in a directed graph? So this is what the problem asks us, that in a directed graph, whether the size of ST minimum cut is equal to the size of TS minimum cut. So you can think about it yourself, and I'll just realize that the answer to this is false, that this statement is false. And I'll give you an example also why is the case. So this statement is false, and maybe you guys can construct the example yourself also, but I'll also just tell you guys. So it's very easy to see. So suppose this was the graph only. It had only two vertices, let's say S and T, and let's say this graph had two edges. One edge was from S to T, and this edge, let's say, had a capacity of 2. So we all edges also have some capacity, right? And similarly, let's say there was another edge, but this edge was from T to S. and this had a capacity of 1. But this has a capacity of 1. So now if we see the size of SG minimum cut, so this is just the graph given to us. In this graph, the size of SG minimum cut will be 2 because we'll need to delete this edge of capacity 2 so that no path remains from source to sink. So size of SG minimum cut will be 2, whereas the size of TS minimum cut. So while finding out TS minimum cut, we have to delete a set of edges such that no path remains from T to S. So from T to S, only this edge is contributing to the path. So we'll have to delete this edge. And this edge has a capacity of 1. So the TS minimum cut will have a size of 1. Whereas ST minimum cut has a size of 2. I hope you guys get the difference because like this edge does not contribute to an ST minimum cut because even if we delete this, after we delete this 2 capacity edge, even if this edge still remains, then there is no path from S to T. Even though there is a path from T to S, we are finding out ST minimum cut. So we just want to delete all the paths which go from source to sink. And T to S does not matter to us. T to S path don't matter to us. So ST minimum cut is of size 2, whereas TS minimum cut is of size 1 in this graph. So from this, we can actually claim that size of ST minimum cut is not equal to size of. There exist examples where size of ST minimum cut is not equal to size of TS minimum cut. Like if both are 1, then we will obtain an example where those are equal. But in general, they may not be equal. So that's why this statement is false. And in the given figure, so while uploading this document, I'll also copy this picture into the document. So in the given graph, the ST minimum cut has size 2, whereas the TS minimum cut is of size 1. So so the given statement does not hold for the given graph. So yeah. So I hope everyone gets this. It's not too difficult to see. So yeah. So I'll just underline the answer also that the answer is 1. Okay. So this was the second question where size of H minimum cut is not necessarily equal to size of TS minimum cut in directed graphs. But suppose the problem was instead this. Now we have come to the third question. So I'll assume that we are over second question now. So now I'm discussing the third question now. So the third question is the same is asking the same thing whether size of ST minimum cut is equal to size of TS minimum cut, but it's asking for an undirected graph. So the second question was for directed graphs, but the third question asks us the same problem for undirected graphs, whether this statement is true or false for undirected graphs. So note that undirected graphs are a special case of directed graphs. So yeah, something like that. But so in an undirected graph, is size of ST minimum cut equal to the size of TS minimum cut? So this statement is true or false. So actually, you guys can also think about it, but I'll tell you guys the answer. That in this case, the answer actually comes out to be true. That uh, the size of ST minimum cut will always be equal to the size of TS minimum cut. And in fact, the minimum cuts will be the same also. And why is this the case? So this can be maybe I can show you guys via a diagram, and then maybe we can discuss this also. So let's assume we are given some sort of an okay. I'll just draw this. So let's assume we are given this cut C. So what this represents is, so a cut is essentially a partitioning of the vertex set into two pieces, right? So suppose we are given so maybe I should mention this also. So cut C, and so here is the set of vertices, let's say A, and this set of vertices is okay. So this has been discussed in the lectures that every cut actually partitions the vertex set into two sets. A min cut partitions the vertex set into two sets, right? Two sets of vertices actually, because deleting some edges makes some component disconnected. And so the disconnected components become actually two sets. So maybe I should move this diagram a little bit. So, yeah. Yeah. So let's suppose the cut C, there was a set of edges which we delete, and these sets of edges actually partition our graph into these two sets of vertices, the sets A and set B. So the set B contains the vertex T, the set A contains the vertex S. So now what actually happens is all the edges which are across this set, which go across this set. So there can be multiple edges going across this set. So this edge, let's say, is E1. This edge is, so this edge is, let's say, E1. This edge is, let's say, E2. And there can be multiple such edges. So like there can be multiple edges going from here to here. So yeah. So now actually, or maybe okay, so there can be multiple edges or multiple capacities going on from A side, going between A side to B side. So note that in a directed graph, what was happening was these edges also had some directions, right? So the edges going from A side to B side contributed to the ST cut, whereas the edges going from B side to A side contributed to the TS cut. So the edges going from B side to A side did not contribute to the ST cut, rather they only contributed to the TS cut. But now in this case, suppose we are given that the graph is directed and suppose the graph is undirected. So edges don't have any directions necessarily. So what actually happens now is these same edges. So if edge E1 was contributing to this A to B cut, this ST cut, then this edge E1 is also contributing to the TS cut as well. Because this edge is going across A and B. So what happens is in undirected setting, this edge goes across as TS in an ST cut also and also in a TS cut. So what this means is that suppose there was a cut given to us, suppose there was a set of edges given to us which disconnects S from T, then same set of edges also disconnects T from S. And the capacity of the cut also remains the same actually. So the capacity of the cut is just sum of capacities of these edges, and this will be the same for like ST or TS setting. So the high level idea is actually all the ST cuts will also actually be TS cuts. So every ST cut corresponds to a TS cut also, because in an undirected graph, deleting the same set of edges will also disconnect T from S as disconnecting S from T. So what this means is that suppose we obtain a cut of size 3 for like ST setting, then we'll also have a cut of size 3 for the TS setting. So always the cuts for ST and TS will be of equal size. The minimum cuts for ST and TS setting will be of equal size. I hope you guys get the intuition from this diagram. I'll also put this diagram into the document and I'll be writing up the solution now. So, so this is true because this is because as if we consider any cut C, so C is just a set of edges uh, which partitions the vertex set into sets A and B such that S lies in A and T lies in B, then the same cut actually, if we consider any ST cut, so suppose we are considering ST cut, so which disconnects S from T. So there is no path from S to T in the graph G minus C. So what we can actually say is that then the same cut then the same cut C is also a TS cut as the graph is undirected. So if there are no ST paths in G minus C, then there will be no TS paths in G minus C either. And obviously vice versa. Like if there are no TS paths, then there will be no ST paths also. So what this actually means is that so any ST cut is also a TS cut in undirected graph. TS cut in undirected graphs. And so what this actually means is that the minimum cuts for ST and TS will also have the same capacity. Because like suppose there was a cut C, which was suppose there was a minimum cut C for ST, then that will also be a minimum cut for TS. So if the cut is same, then its capacity is also same, right? So that's why this statement is actually true that in an undirected graph, size of ST minimum cut is actually equal to size of TS minimum cut. So yeah, so I hope this is clear to everyone. So I had one more thing to discuss regarding this problem. I'm not able to recall that right now. Okay, maybe this was what I just intended to discuss. So yeah, so I hope everyone gets the difference between directed and undirected settings. So we can have directed graphs where ST minimum cut and TS minimum cuts have different sizes, but yeah, in an undirected graph, the sizes will always be the same. So yeah, so one thing which you should note is so one important property which you guys should note, although I believe you guys would already know this, but still, I'll just put it out there. Uh, One important property is that uh, so there can be actually multiple. So in a graph G, there can be multiple ST cuts. So there can be multiple actually minimum ST cuts also. So minimum ST cut is just a cut of minimum size, right? Just an ST cut of minimum size. So there can be multiple ST cuts which have minimum size. The only thing which will be common to them is that they will all have the same size. So there can be multiple ST minimum cuts in a graph However, all will all the minimum cuts will have the same size. So because if two cuts have different sizes, then actually one of them is not the minimum cut actually. So yeah, there can be multiple S3 cuts, but they will all have the same size. So one example which we can give for this is also a very straightforward example. So maybe I can just copy this diagram and yeah. So suppose was another vertex and I actually call this vertex as S instead of this vertex. And suppose I give an edge like this from S to this vertex. So in this example, and suppose this edge has a capacity of 2. So in this example, it can be actually seen that this deleting this edge also causes if we delete this edge, then there exists no path from S to T, right? So this edge consists of an SG cut. So this SG cut has just a size of 2. But similarly, suppose if we just delete this edge instead of this edge, so let's say this is U. So suppose instead of this SU edge, suppose we delete the UT edge. So what happens is if we delete this edge, then also there does not exist any path from S to T, right? Because from S we can go to U, but from U we can't go to T if this two cars is deleted. So this UT edge also forms one SG cut. And similarly, this SU edge also forms one SG cut. So these are both actually minimum SG cuts, but both have the same capacity actually. So in this graph, there are two minimum SG cuts, but both actually have the same capacity, right? So for example, in the given figure, so figure I'll paste later. mm, the edge SU forms one minimum. So the edge SU is an ST cut of size 2. Similarly, the edge UT is also an SG cut of size 2. So there are two minimum ST cuts in the given graph, and both have a size of 2. So yeah, so both of these have a size of 2, but these are two different SG cuts, but they will have the same capacity. So I hope you guys get the gist of what I'm trying to say here. So this is one important property, and why is this important? Maybe it can come later, but yeah, just keep in mind that there can be multiple SG cuts. But the minimum cuts will all have the same size, even though there can be multiple minimum SG cuts. So yeah. So now maybe we can move on to the fourth question. So the fourth problem says that consider the following network given below with source S and sink T, with the numbers on the edges denoting maximum capacity across a particular edge. So we are given this network, and the number on all of these edges represents actually the capacity of that edge. And now we want to increase the flow from vertex S to vertex T. So what we actually want is so in this network, there will be some flow going from S to T, right? So we can find out the maximum flow in this graph. And actually, if you calculate the maximum flow for this graph will come out to be equal to 2. Or I believe it would be equal to something like 3. So in this graph, something like the minimum cut will come out to be size of 3 or something. But now what we want to do is we want to add an edge, add further edges in this graph so that the maximum flow from S to T now increases. So whose edges, which cup, like what edges should we have, like which edges should we increase capacity of such that the maximum flow in this graph actually increases from, let's say the flow is max flow in this graph is currently 3, and now we what we want is actually to increase it from to more than 3 or something like this. So this is what the problem is saying. So I believe okay, so someone has joined us. So hello Dhruvika. So since you have joined just now, so I'll just give you a gist of what has been discussed so far. So far I've just discussed like 3 problems related to like minimum cuts only. So this week we are discussing problems related to minimum cuts and the Maslow min cut duality. And this has so these problems are based on the lecture, this week's lectures, which were like, I'm assuming that you have already seen the lectures, and now we are discussing about problems related to SG macros and min cuts. So yeah. So till now we have discussed 3 problems. So maybe you can watch the recording later to see what these 3 problems were. So now currently I'm discussing this 4th problem now. So we can start from this again. So the problem says that we are given a flow network with each edge having some capacities, and these capacities are given to us. And now what we want to do is we want to increase the flow from vertex S to T. So we already know in this graph, we can find out the max flow from S to T, right? In this graph, we already know what the max flow will be. We can find out via forceful Gaussian algorithm, and it will come out to be equal to 3. The max flow in this graph will come out to be 3. You can check that later. And now what we want is an edge is called a bottleneck edge if the flow from S to T increases upon increasing the capacity of that edge. So now we want to select the bottleneck edges from the below given options. So what we actually want is so suppose we are given all these edges and there is some maximum flow in this graph which will be present from S to T. And now what we want is we want to select one edge and increase its capacity so that the max flow from S to T increases. So this is what we actually want. We want to increase capacity of an edge such that max flow, uh, the value of max flow increases upon increasing the capacity of that edge. So now the problem statement says select the bottleneck edges from the given options. So there can be multiple edges actually. So we want to select all possible edges such that on increasing the capacity of that edge, the max flow from S to T increases. So I hope the question is clear. So if the problem is not clear, you can message me. You can type in chat and let me know. So I'll try to explain it again if it is not clear to you. So yeah. Okay, it's clear. Nice. So let's see what ideas can be employed here. So we already know from the we already kind of know from the maximum min cut duality that the size of maximum flow is actually equal to size of minimum cut, right? Maybe I can type this down as I say this also. We know that the size of ST maximum flow is equal to the size of SG minimum cut. So this is what we know from lectures. This is the maximum min cut duality. So if we want, so what this actually means is that if we want to increase this thing, if we want to increase the size of maximum flow, which we want in this problem, we want to increase the flow from vertex S to T. So we want to increase the maximum flow. We should write like this. So we want to increase the maximum flow. And since this is equal to the minimum cut, so what we can actually do is instead of increasing the maximum flow, we can just increase the minimum cut. And this should also give us the same answer. So I hope what I'm saying is clear that size of ST maximum flow is actually equal to size of ST minimum cut. So to increase the size of ST maximum flow, what we can do is just increase the size of minimum cut. But note that there can be multiple minimum cuts. That's what I was discussing initially, right? There can be multiple minimum cuts in a graph, but all will have the same size. So to increase the maximum flow, we'll actually have to increase size of all possible minimum cuts, not just one minimum cut. But luckily, we'll see in this problem that there is exactly one minimum cut. So this will save us a lot of headache. So that discussion of multiple minimum cuts is for another day. So the key idea here is that to increase the size of maximum flow, we need to increase the size of minimum cut actually. So increase the size of ST max flow, we can just increase the size of ST min cut. So I'm calling maximum flow as max flow and minimum cut as min cut. But what actually is size of a min cut? So size of a min cut is just the sum of capacities of edges going across that cut, right? So there are some edges, let's say E1, E2, E3 going across a minimum cut. Then if we increase the capacity of any of those edges, so suppose example, in this problem, suppose in this diagram, so this was the cut C which partitioned the vertex into vertex sets A and B. So, and this was, let's say, the min cut, and this was the edges going across the min cut, E1, E2, and some edges in between. So if I increase capacity of any of these edges, so if I increase the capacity of E1 or E2 or any of these edges, then actually the sum of capacities of edges going across A and B will also increase, right? Because the capacity of this cut is just the individual sum of capacities. So even if one edge has increased capacity, then uh, the whole cut will have increased capacity. So what this means is that so if we are able to find a minimum cut, we can increase its capacity by increasing the capacity of any edge of that minimum cut. So I hope this key observation is clear. So to increase the capacity of an SG min cut, we can just increase the capacity of any of the edges of that SG min. So maybe I should write it down a bit more in terms of variables. So to increase the capacity of an SG min cut C, we can just increase the capacity of any of the edges of C. And by this, we'll be able to increase the capacity of C actually. And this is what we want to find out the maximum flow. So we want to do this for all possible SG min cut C because there can be multiple min cuts. Suppose there were two possible min cuts of size 3. So if we increase the size of first min cut by, so for example, let's say in this graph. So in this graph, we sort of, as I was previously discussing, so suppose we are given this graph and in this graph, we sort of already know that there are two possible SG min cuts, right? So this edge is part of one SG min cut because deleting this edge causes SNT to be disconnected, and this cut has a capacity of 2. Similarly, deleting this edge also makes SNT disconnected. Like there is no path from S to T if we delete this edge. So this edge also forms a cut of size 2. But what this actually results in is that there are two possible cuts. So to increase the maximum flow going from S to T. So right now the maximum flow going from S to T will be a flow of 2, as it can be seen easily also. But to increase the size of the maximum flow, we'll have to increase the size of all possible min cuts. So this is one min cut. So so we'll have to increase the capacity of this min cut from 2 to something more than 2. Suppose we increase it from 2 to 3. So this cut now has an increased capacity of 3. But still, because of this min cut, if this still has a capacity of 2, then the resulting graph will still have a maximum flow of 2 only. Because then this will still be a min cut. Similarly, if we just increase the capacity of this edge, then because of this edge, the min cut will still remain 2. So what we'll actually need to do is increase the capacity of both of these edges. If we increase capacity of both of these edges, then only we can claim that the maximum flow will increase in this graph. So I'm just giving you one example. This sort of situation will not arise in our question, but just giving you this example that you need to keep in mind situations like these also. But this is a story for another day, like identifying all the edges whose capacities which we need to increase. So this can also be done, but I'll not be discussing that in this lecture. So, so in this tutorial, so what we just want, so what we'll actually get is, so here there were multiple minimum cuts possible. But what we'll get in this problem is there will be just a unique min cut. And since you, so I'll give you guys this as a homework to find out what's the, not as a homework, but something as an exercise to try it yourself, like what will be the min cut, like what will be the edges going across it and so on. Or maybe I'll just inform you guys what actually is the min cut, and I'll leave it up to you to compute it by yourself also to verify whether what I'm saying is correct or not. Okay. So to increase the capacity of any min cut, we can just increase the capacity of any of the edges of C. So if there are multiple min cuts present in G, then we need to increase the capacity of all the min cuts. But in the given graph, so in this given graph G, there is exactly one min cut. There is exactly one SG min cut of size 3. And what's that SG min cut? So I leave it up to you guys also to verify this. But what I'm claiming is this is an SG min cut of size 3. This CT edge, this AD edge, and this BD edge. So when these three edges are deleted, so the direction in which my cursor is moving. So this is a cut of size 3. And what I'm claiming is that this will be the unique minimum cut. So there will be no other cutoffs, no other SG cut of size 3 in this graph. And you can verify this yourself also later that you won't be able to find any other cut of size 3. So what I'm claiming is this is the unique cut of size 3. And this is actually the minimum cut. So we just need to increase the capacity of this cut. And the edges going across this cut are the edges C, T, A, D, and B, D. So increasing capacity of any of these edges will result in an increase in the min cut. So the correct options will be something like this. C, T, maybe I should write T in small because C, T is part of this min cut. The A, D is also part of this min cut. So A, D can also be increased. Similarly, B, D can also be increased. So note that any of these three edges, when their capacity is increased, this A, D, B, D, or C, T, the size of SG max flow will increase in this graph. This is because on increasing capacity of, let's say, B, D, the size of SG min cut will increase in the graph. And as the size of min cut increases, the size of max flow will also increase. So yeah, so this is the high level idea of how to solve this problem efficiently. One very brute force idea would have been maybe just go option by option, maybe C, the edge B, C, and just like increase the capacity of B, C from let's say 1 to something like a 2. So let's say we increase the capacity of the edge B, C from 1 to 2, and then recalculate the max flow in the graph. And if it comes out to be greater than 3, then you can say that increasing capacity of B, C increases the max flow. Similarly, For A comma D, you could have checked yourself, like set its capacity from 1 to 2 and see whether the max flow initial in this graph is actually 3, whether it increases from 3 or it does not. So the brute force technique would have been to go option by option. But what I've told you is a bit smarter technique to look at all the min cuts and uh, increase capacity of any of the edges. But here also there's a catch that there can be multiple min cuts, so we need to increase capacity of all min cuts. But in this graph, you will have a very special property that there's exactly only one SG min cut of size 3. So we just need to increase the capacity of any of these edges. So you can verify this yourself also that if you have the time later to verify the answer that AD, BD, and CT are the only edges. On increasing whose capacity, the graph will uh, become a higher capacity graph. Like the graph will have a higher maximum flow. So you can see yourself also like suppose take BA edge and just increase its capacity by 1 and see whether the max flow changes or not. Suppose take DT edge and increase its capacity and see max flow changes or not or something. And you will actually see that only these are the edges which will be important for us. So yeah. So I'm not writing down the brute force approach because brute force approach is easy to see. Just increase capacity of all edges 1 by 1, take these 6 options and just find out what's at stake. So yeah, but I'm just writing down this smarter approach. So we need to increase the capacity of all the min cuts. There's exactly one SG min cut of size 3. This is the cut. So what's the cut? So this cut contains the edges C comma T, A comma D, and B comma T. C comma T, A comma D, and B comma T, B comma D. And I'll say that I'll just put this in fold that verify this yourself. By finding out the SC min cut as discussed in the lectures. So yeah, something like this. Yeah. Okay, so maybe I should put this in other lines to make it a bit clear. So yeah. So what this actually means is that if we are able to obtain this graph, hence increasing the capacity of any of the edges C comma T, A comma D, or B comma D will increase the size of SG min cut and hence increase the SG max flow in G. So what's the correct answer? So what the correct answer are? So options B, C, and F are correct. So options B, C, F are correct. So I hope what I was trying to say is clear. If it is not, maybe you can, Vika, you can ask me via chat and I'll try to explain it a bit better also. So yeah, but this is the high level idea. We get that options B, C, and F are correct here. Okay. So now maybe we can move on to fifth question then. So if you don't type anything in chat, I'll just be assuming that everything is clear, my voice is okay, my screen is okay, and so on. So if you have any issues, you should type in chat. So now maybe we can move on to the fifth question. So Fifth question asks us, let G, so G is a graph with vertex at V and H at E. Let it be an undirected graph with V as vertex at and E as H at. Let C is equal to S comma V minus, so V minus S be a minimum cut in a flow network. So this is just the, so a minimum cut is just a set of edges. So it can be denoted by a part. So as I told here also that a minimum cut can be considered as the set of edges also. So you can call the set of edges as the cut, or some people also like to refer to as the partitioning of the vertices as the cut. So like because deletion of these edges causes the vertices to be partitioned into two sets, right? So some people like to refer to the cut as this partition of vertices. Some people like to refer to the cut as the set of edges. So both things are okay. So here, so it would be problem dependent. Like it can be easily deduced from the context of the problem, like what the problem is referring to. So here the problem says that S comma V minus S will be the partitioning of the vertices induced by the set of edges of the minimum cut, right? So C is equal to S comma V minus S be a minimum cut in a flow network. Now we need to answer whether the following statement is true or false. So if we increase the capacity C, if we strictly increase the capacity C of every edge across C, then the maximum flow of the network must increase. So I've kind of discussed this thing before this also. So would you like to try this out, Dhruvika? This is question whether this statement is true or false. I have discussed something like this in the previous questions also. So the problem says that if we strictly increase capacity C of every edge across C, then the maximum flow of the network must increase. So even if you don't know the correct answer, you can just tell me what do you think should be, whether the statement should be true or should it be false. Like what's going through your mind. You can just type anything if you want. Okay, so Dhruvika is saying that the Dhruvika thinks that the answer should be true. That if we increase the capacity C of every edge across C, then the maximum flow of the network must increase. So Dhruvika, actually, I think this statement is not true, but actually incorrect. So I'll give you an example also. So, so the problem actually says that uh, we are only increasing the capacity C across are going across a minimum cut in a flow network, right? So suppose we take this example only, as I discussed earlier. So this forms one minimum cut. This forms one. So here the problem actually says that so like I told earlier also, like what we have to do to increase the maximum flow is actually to increase the capacity of all minimum cut C. So here what we are given is one minimum cut of the flow network. C is a fixed minimum cut, and we are increasing the capacity C of every edge across this minimum cut. But it does not mean that we are increasing the capacity of all possible minimum cuts. So I hope you get what I'm trying to say here. So, so what I'm trying to say is, so we are given an undirected graph, right? So maybe I should just draw the example of an undirected graph instead. So let's consider this graph, and instead of this, just take this edge of capacity 2. Similarly, just take this edge of capacity 2. So now what actually happens is this SC wedge also forms an ST cut. and this UTH also forms an SG cut, right? So suppose the cut C, which was given to us in this problem, was this cut, which had S on the source side and this U and T on the sink side. So only this edge was going across that cut. So now what we do is suppose we increase its capacity from 2 to 3. Suppose this edge becomes an edge of capacity 3, but this remains a capacity of 2, capacity 2 edge. So still the maximum flow in this network will be 2 because the capacity of this cut does not, the size of this cut does not increase. So that's why actually what we need is to increase the capacity of all the minimum cuts, not just one minimum cut. So there were two minimum cuts, so we need to increase the capacity of all the minimum cuts, and only then we can say that the maximum flow will increase. So the answer here is false, and it can be seen in the given figure. So I'll place the figure later. False. So I'll just underline the correct answer. So in the given figure, it can suppose S is the source side vertices. Suppose S is just the source side vertex S. Then what we can actually say is so what we can actually say here is suppose S is the smallest, so V minus S will be just the set of U comma T. So if we increase the capacity of the edge, if we increase the capacity of SU edge, so this was the SU edge from 2 to 3, from 2 to 3, the SG max flow still remains equal to 2. So that's why this is sort of a counterexample, and so the capacity does not increase. So the max flow does not increase. Hence the given statement is. Okay. So okay, so Dhruvika is saying that she gets it now, so that's good. So another interesting problem now. So suppose so this is something so this is something try it yourself. It's also an interesting thing. I'll also discuss this. So suppose what we do is instead of strictly increasing capacity C of every edge across C, suppose we just increase the capacity of every edge. So suppose we increase the capacity of, suppose we strictly increase the capacity of every edge in G, then does the maximum flow increase necessarily? Suppose if we increase the capacity of every edge, then does the maximum flow necessarily increase? Yes or no? So what do you think should happen in this case, Dhruvika? So instead of, so what we were earlier doing was increasing the capacity of every edge across C only. The edges which were going across this cut C. So only this edge we are increasing capacity. But instead, let's just increase the capacity of all the edges. Suppose we increase its capacity from 2 to 3, its capacity from 2 to 3. So can we always say that the maximum flow will increase? Okay, so Dhruvika is saying the answer should be no here. So I believe in this case, actually, Dhruvika, the answer would be yes, that in this case, actually, the max flow will always increase. Yes. And why is this the case? So you can think about it yourself also, but um, what what we are actually doing is, so we discuss in this problem, right? to increase the capacity of an ST. So we discussed here that we need to increase capacity of all the min cuts if we want to increase the capacity. If we want to increase the maximum flow in network, what we need to do is we need to increase the capacity of all the min cuts. And if we are increasing capacity of every edge, so every min cut has some edge in it, right? So there, every min cut has some edge in the graph, has some edge of the graph going across it, right? So what this actually means is that there will be at least one. So, and every edge has an increase in capacity. So what this actually means is that so every min cut has an edge going across it. And if we are increasing the capacity of that edge, then actually the capacity of that min cut is also increasing. So you get what I'm trying to say here? So this is because the size of every min cut increases. Every min cut of G increases as there will always exist some edge E going across the min cut. And so let's just say here that Z is also connected. Just to, and so mm, increase in capacity of E causes an increase in size of cut. So I hope this argument is clear that. So to increase the max flow, actually what we want to do is increase size of all the min cuts, right? And every min cut will have some edge going across it, right? Because there will be some edge always going across the min cut. So, and since we are increasing capacity of every edge, so every edge going across the min cut will have an increase in capacity. And because of this, the size of that cut will also increase. Size of all cuts increases, so that's why size of min cut also increases. I hope I'm making a bit of sense here. Now maybe we can move on to the sixth question then. Okay, so sixth question says that uh, so in this problem we're given that we need to remove some of the edges from the given graph G to make the vertices S and T disconnected. So G is given to us, and since edges don't have directions, it's an undirected graph which is given to us. And now what we need to do is we need to make the vertices S and T disconnected from each other. So what we actually want to find out is an ST cut, and the cost of removing edges is equal to sum of capacities of the edges. And we want to find out the set of edges which make it disconnected with minimum cost. So what we essentially need to find out is an ST minimum cut. So these are the four options, and we want to find out which of these are actually ST minimum cuts, right? So note that again, there can be multiple ST min cuts. So what we are going to do is we are first going to find out one ST min cut, and one ST min cut can be found out using Ford-Fulkerson algorithm, like this was discussed in the lectures also. Like how do we find one ST min cut? So one ST min cut can always be found by us. And then if we need to verify whether like, and then we have these four options. So what I'm trying to say is, suppose we find out one ST min cut in this graph. Suppose we find out that there exists a cut of, let's say, size 4, and that's the minimum cut in the graph. So suppose there is a cut of size 4, which is the minimum size cut in the graph. Then what this means is that any cut, any ST cut which has a size of 4 will also be a minimum cut. Will also, so there can be two cuts of size 4. two ST cut size 4, and then both will be minimum cuts. So what I'm trying to say is we first find out one ST minimum cut in this graph. And then we just check option by option whether all of these options form an ST cut and whether they have the same cost as the minimum cut or a higher cost. So if they have a higher cost, let's say minimum cut was of size 4, but some of these cuts have a size of 5, then we'll say that they are actually not the minimum cut because a minimum cut should have a cost of 4. Because all minimum cuts have same cost, even though the cuts can be different, but the cuts should have the same cost. So I hope this sort of statement is clear. So what we are going to do is we first find so one SG min cut of the graph G using the algorithm. So it's just sport focus on algorithm only discussed in the lecture. So we just find out the SG minimum cut using the size of SG minimum cut using sport focus and algorithm. And then what we actually do is then we check option by option whether an option forms an SG cut with the size of cut being equal to the size of the min cut. So something like this. So I hope you get what I'm trying to say here. That initially, so by our algorithm, we can only find out one SG min cut, or let's say we can just find out the size of the SG min cut by the algorithm discussed in the lectures. But we still don't know whether these edges form an min cut, these edges form an SG min cut, these edges form, or these edges form. So what we actually do is we first find out the size, and then option by option we check whether these two edges actually form a cut and what's the size of that cut. So if the size of that cut is actually equal to size of the min cut, then these edges are indeed forming an ST min cut. Similarly, for these three edges, we will check that whether these three edges on deletion form a cut, and if they form a cut, whether this cut has a size equal to the size of min cut. Similar thing here, similar thing here. So once again, in this problem, uh, I'll just state what's the minimum cut in this graph directly, and I'll leave it to you guys to uh, figure out actually why is that the cut. So maybe I'll just do it a bit orally so that to be a bit faster. So yeah. So what I'm actually claiming here is so the first step is just to find out one estimate cut and using the algorithm discussed in the lectures. So what actually you can find out is using the algorithm of the lectures, we can see that the SG min cut is of size 4. And the cut which we will obtain is this cut, which contains the edges FG, FI, and HI. So, and contains and consists of the edges this FG, FI, and HI. So this, the direction of my cursor is the SG min cut. So you can see this also that these FG, FI, and HI actually these three edges form a cutoff capacity 4 only because 2 plus 1 plus 1 is 4. And you can see that on deletion of these three edges, there will exist no path from S to T because these G, I, K, T, J will be in one part of the graph, and this H, F, D, E, C, A, S, B will be in one part of the graph. So this is a cut of size 4, and this is the minimum SG cut in the graph, and consists of the edges. So the edges of this cut are F, G, F, I, and H, I. F, G, F, I, and H, I. So actually, this is the min cut, and this can be obtained via the fourth full question algorithm. So actually, option D is one SG min cut. And now we want to find out whether other options also form SG min cut or not. So our target will be to check for options A, B, and C whether they form an SG cut, and if they form an SG cut, whether they form a cut of size 4 or their cut size is more than 4. So option D is a. So we already know that we have found out one SG minimum cut, but there can be multiple. So we need to find out other also from these options, other minimum cuts also from these options. Option D is an SG minimum cut. Now we check for other cuts option by option, right? So option A is these edges ij and ik. So this edges ij and ik. So what do you think, Dhruvika? Do these edges ij and ik form an SG cut? So on deletion of these two edges, so these are the edges ij and ik. So on deletion of these two edges, do S and T become disconnected? So if we delete these two edges together, will S and T remain connected or will they become disconnected now? So would you like to answer this, Rui? So on deletion of these two edges, whether S and T remain connected or become disconnected? Okay. Okay, so Dhruvika is saying disconnected. So yeah, so nice job, Dhruvika. So actually you are correct. So if these ij and ik edges are disconnected, then it is actually easy to see that if these two edges were not present, then this T, J, and K will form a single component, and all of these vertices will be in another component. So there will exist no paths from S to T if we delete ij and ik. So we know at least that uh, these ij and ik form an SG cut. So these two edges at least form an SG cut, and now we want to find out whether are they forming a minimum cut or not. So to verify whether they form a minimum cut, we need to check whether cost of this cut is actually equal to 4 or not greater than 4. So if this cut has a size of greater than 4, then this will not be a minimum cut. But if it has a size of 4, then it will be a minimum cut. And it can be seen easily that this ij and ik, both edges are of size 2. So 2 plus 2 is actually equal to 4 only. So size of this cut is nothing but 4. So actually this also forms the minimum cut. So it can be easily seen that these edges form an SG cut of size 4. Hence, this is also an SG minimum cut. So option A is also an SG minimum cut. So now let's check for option B. So option B says the edges which we delete are Fi, Hi, and Ij. So what are these edges? So Fi, Hi, and Ij. So we are deleting these three edges. So this edge Ij is being deleted, this edge Fi is being deleted, and this edge Hi is being deleted. So we are deleting these three edges. So what do you think, Dhruvika? Would you like to answer whether the graph after deletion of these three edges, whether there exists a path between S or T, or will they become disconnected in this example also? So note that the edges being deleted are this edge, and this edge. This Ij, Fi, and Hi. So will they become disconnected or will they remain connected even after deletion of these three edges? Yes, SNT, because we are looking for an ST min cut, so we'll need to answer whether SNT become disconnected or. Okay, so Dhruvika is saying that they will remain connected. So yeah, good job, Dhruvika. So you are correct actually that if we are deleting just these three edges, then there will still exist a path through this G, I, K to T. And from S to G, we can go on without these edges. So actually, you are correct that even if we delete these three edges, SNT won't be disconnected. So this set of edges actually does not even form a cut. So it can form a min cut, right? If it is not even a cut, how can it be a minimum cut? So it can be seen that these edges do not form an ST cut. So this option is incorrect because we need to check which edges form a minimum cut, and if they don't even form a cut, then how can they form it? And option C was this edges C, E, D, F, and D, E. So C, E. So again, over to you, Dhruvika. D, F, and D. C, E, D, F, and D, E. So this edges along which I'm moving the cursor. So these three edges, will they form an ST cut or not? So after deletion of these three edges, will SNT remain connected or will they become disconnected? So Dhruvika, what do you think should be the answer here? If we are deleting these three edges, D, F, D, E, and C, E, does there remain a path or will they become disconnected after deletion of these three edges? These vertices S and T. Okay, so Dhruvika is saying disconnected. So yeah, good job, Dhruvika. You are again correct. So actually, if we are deleting these three edges, then this component separates out this DC, ACB, ASB component. This component separates out on one side. This component separates out on other side. So actually, this set of edges actually forms an SG cut. But now we need to verify whether it forms a minimum SG cut. So, so we just need to find out the size of this cut. So actually these three edges, so this cut will have a size of actually 1 plus 3 plus 1, which will be 5. But minimum cut has a size of 4. So even though these edges form an SG cut, they are not forming an SG minimum cut because minimum cut has a size of 4, but these edges form a cut of size 5. So even though these edges form an SG cut, the size of the cut is equals to 5, which is, and hence it is not an SG min cut, as size of min cut is equals to 4. And why was this 4? We had already got this using algorithm of the lectures. So yeah, and maybe I should write this then, that you guys should verify this yourself. Verify this yourself. So yeah. So essentially, we get that option D is naturally an ST minimum cut. Option A is an ST minimum cut. B and C are not. So only options A and D are correct. So I'll just write down the answer also. Hence, options A and D are correct. Okay. So now, so I hope this question is clear. So now maybe we can move on to the seventh question then. So I had 9 questions prepared, but maybe I will not discuss the ninth question. So we have 2 questions left now to discuss, the question 7 and question 8. Okay. Okay. Yeah. So seventh question says that you have been given an n cross n chessboard. This problem will involve placing rooks on a chessboard so that they cannot attack each other. So I hope everyone who's watching this video has played chess before. If you have not, so rooks are pieces on a chessboard. So chessboard is a square of n cross n size, and uh, rook can attack. So what rook can do is it can move along the same row or along the same column. So if a target is in the same row as the rook or as in the same column as the rook, then rook can attack the target. So the problem involves placing rook on a chessboard so that no two rooks can attack each other. So like if we place three rooks on three squares, then no two of those rooks should be attacking each other. So now we want to find out the maximum number of rooks that can be placed on the chessboard such that no pair of rooks can attack each other. So the options are also given to us, although I don't know if options are needed here. So maybe I can move the options here. Yeah, now it's a more interesting problem. So, Dhruvika, would you like to again answer this? Would you like to like at least attempt it? Like what any thoughts or comment like what should be the answer here? So we are given an n cross n chessboard, so there are n uh, squares present on the chessboard. So n square small squares are present on the chessboard. And now we need to place rooks on the chessboard so that they cannot attack each other. And we want to find out maximum number of rooks that can be placed as a function of n. So any guesses, Rubika? Like, is it n? Is it n square, root n, n by 2, n by 5? Okay, sure. So Rubika is saying that she's thinking. So yeah. So we have a fair bit of time. You can take your time. So I'll mute myself while Rubika thinks. Okay, so Dhruvika is saying that the answer should be n. So yeah, good job, Dhruvika. Actually, the answer is correct. That answer should be n only. So yeah. So and the idea is actually so we want to find out the maximum number of rooks that can be placed, right? So to find out maximum, what we essentially need to say is we want to give a placement in which we actually obtain n rooks. And we also want to say that there cannot exist a placement where more than n rooks can be placed. So like what I'm trying to say is we want to find out the maximum number of rooks, right? So to show that this is the maximum number of rooks that can be placed, we need to give an example. We need to give we need to give a placement where n rooks can be placed, and we need to show that more than n rooks can never be placed. So what we need to show is that we need to show that n rooks can always be placed and more than n can never be placed. That's why the answer is N for us, right? Maybe I will give this right proof. So, so these are the two parts we need to show. First, we need to give a placement where n rooks can be placed. And second part, we need to show that more than n rooks can never be placed. So since Ruika gave the answer as N, so let's hear it from Ruika. Like, so why do you think, Ruika, that so what is the placement for the n rooks? So suppose we want to find out n rooks. So okay, so Dhruvika has already written in chat that we can place all of them diagonally. So yeah, correct, Dhruvika. So part one, uh, to show the uh, so it can be actually, so maybe I should draw a diagram for this also. Okay, so I don't know how to draw the squares, how to draw chessboard, I don't know. So maybe I'll just draw a chessboard like this. Yeah. Suppose there was this 4x4 chessboard. So suppose n is equal to 4 right now. So the four rooks, if we want to play, so we want to place four rooks, right? So let's say these are the rooks. These four circles are the rooks. Then these rooks actually, Dhruv is saying, can be placed along the diagonals. So yeah, it can actually be seen that if we place these four rooks along these diagonals, then no two rooks actually can kill each other because rooks can only move along the same column or rows. So no two rooks share the same column or row. So that's why for n equals to 4, so this can be generalized to n also, but specifically for n equals to 4, it can be seen that four rooks can be placed along the diagonals and they won't be killing each other. So yeah, so it can be easily seen that n rooks can be placed along the diagonals and so will never attack each other. And also now, so first part is clear. So first part is clear, Fajrika. So second part is we also need to show that more than n rooks can never be placed. Right. So this part we can show by contradiction to prove that more than n rooks can never be placed. We use contradiction. So what is contradiction? So suppose we can place more than n rooks. Suppose so more than n rooks means like suppose we can place more than n rooks such that no two rooks attack each other. Right? More than n rooks. So let's say, so basically let's say the number of rooks are n prime. And n prime is actually greater than n. That's why we are saying that number of rooks placed is greater than n. So suppose here only we see in this diagram, suppose in so there this was a 4x4 square. And suppose if we need to show that we cannot place five rooks in this square, right? We need to show that five rooks cannot be placed in this square. So how can we go about is that one thing we observe is, so there are four columns only, right? So there are four columns given to us. So suppose we are placing five rooks in this square. Suppose we are able to place five rooks. So then can we claim that since there are only four columns, but we are placing five rooks, so can we say, Dhruvika, that at least two rooks will be in the same column, will lie in the same column? I suppose I had to, so these were the four rooks and there was a fifth rook also. If I place that rook anywhere, then can I always say that rook will share a column with another rook? Yes, exactly. So the rook is saying yes. So actually, suppose if we had n plus one rooks, suppose we could place n plus one rooks in a square in an n cross n chessboard, then we can always say that some two rooks will always share a column with each other because there are only n columns and there are n plus one rooks. So at least two things will be sharing each other. This is what we call the pigeonhole principle, if you have studied about it. So what does this imply? This implies that two rooks are in the same column, and if two rooks are in the same column, then they are actually attacking each other because rooks can move in a column. And so this means that we arrive at a contradiction. So initially we assume that uh, assume that more than n rooks can be placed such that no rooks attack each other. But now we have shown that uh, this is a contradiction. So let's just complete the argument. Let's say the number of rooks is n prime, where n prime is greater than n. Now, since there are only n columns, but n prime rooks, we can always say that there will exist a column in which at least two rooks lie. And this is because suppose if in every column only one rook was present, then there cannot be more than n rooks. Because there are n columns, if one rook in every column, then there can be n rooks. But we have n prime rooks, which are greater than n. So there will be a column in which at least two rooks lie. But this is so this is also called the pigeonhole principle, if we have heard about it. Otherwise, this is straightforward, easy to see from logic also. But this is a very cool principle. You can study about it. Also known as the pigeonhole principle. So this means that at least two rooks lie in the same column and hence can attack each other. So, so we initially assumed that no two rooks attack each other, but we have shown that we have proved that they will attack each other. So we arrive at a contradiction. And what this means that hence more than n rooks can never be placed. So first we showed that n rooks can be placed along diagonals, and we have shown that more than n rooks can never be placed. So what this means is that we have proof. Hence, just like this, hence proof. So yeah. So I hope this is clear. The line of argumentation is clear. So note that I'm handling things a bit formally because this is sometimes what we need to find out whether to ensure that something is maximum. We need to also show that we just don't need to show that this thing is possible. We also need to show that something greater than this is not possible. So this is also an important part of the argument. So yeah. So that's why this is done. Now comes the last question of the day. It's also a very interesting question. Like I personally like this question a lot. And yeah. So it's a short question only, but yeah, it's interesting. So suppose in a directed graph G, so suppose we are given a directed graph G, and let's say we are given that size of ST minimum cut is equal to K. So if S is source and T is sink, then the minimum cut is of size K, and the size of TU minimum cut is also K. So there is a vertex U also. So there is vertices S, T, and U. And if we take S as the source and T as the sink, then minimum cut is of size K. If we take T as the source and U as the sink, then also minimum cut is of size K. Then the problem claims that the size of SU minimum cut is also equal to K. Is this true or false? So what we are claiming is we are just given that size of SG minimum cut is K. We are also given that size of TU minimum cut is K. And then we have to find out whether size of SU minimum cut is also K or not. So we are given ST and TU, and we need to find out about SU. Okay, so maybe I should write it like this. So this is not even greater than equal to. Yeah, not exactly equal, but maybe greater than would make a bit more sense. So maybe I can answer this myself because yeah, this is an interesting question. So yeah, if you want to try it out, you can answer in chat, Ruvika. Meanwhile, I'll also start discussing about this. So actually the answer to this is true, that this will indeed always be the case that uh, if ST minimum cut is of size K and TU minimum cut is of size K, then SU minimum cut may not be exactly equal to K, but it will always be something like greater than equal to K. So that's what we are claiming. We are not claiming that it is exactly equal to K. We are claiming that it will be greater than or equal to K. Like it can never be less than K. That the size of SU minimum cut can never be less than K. This is what we are claiming. And how do we claim this? So this is an interesting argument. Maybe you should pay attention to this. Suppose this. So again, we can sort of show this by contradiction. Like this is true. So how do we prove this? We can show this via contradiction. Suppose size of SU minimum cut. So what will the contradiction to this? So this statement is saying that SU minimum cut is greater than equal to K. So contradiction will be suppose size of SU minimum cut is less than K. Right? So let's just let's just consider this cut. Let's just consider this SU minimum cut, which has size less than K. So okay, maybe I should just copy this diagram. Okay, maybe not exactly. I should just. So what I'm drawing, why this is are actually the sets of vertices which are being bipartitioned. So the partitioning of vertex sets I'm drawing via these. So these are just the cuts, and so we are given that SU minimum cut has size less than K, right? So now what I'm doing is I'm just taking that cut. So let's just consider the cut which has size less than K. So where S lies in this side and U lies in this side. So what we have is an SU cut, and this cut has size less than K, which is already given to us. Suppose size of minimum cut is less than K. Suppose this is what we call the A side of the cut. And this is what we call the B side of the cut, right? So, so now one thing to note is, okay, so these are the vertices S and U, right? And we know that size of this cut, the size of edges going from S to U side is less than K. This is what we know. But now let's just think about uh, the vertex T. So we are also given along with this S and U, we are also given some information about the vertex T, right? That ST minimum cut is K and TU minimum cut is K. So Now, where will the vertex T lie? So there are two cases of vertex T, right? That suppose there is this vertex T, so it can lie. So this is a bipartition. So like some vertices are on A side, the other remaining vertices of the graph are on B side. So this vertex T will either lie on this side or will either lie on this side. So it will lie on A side of the SU minimum cut, or it will lie on the B side of the SU minimum cut. Suppose it lies on this A side. So there are two cases, we will see both cases. So in case one, suppose this T lies on A side of the, sorry for that. Suppose vertex T lies in this side. So now can we say that this cut, the edges going across A to B, they were part of an SU cut, right? So Dhruvika, can we say that these edges are also forming a TU cut? Like the edges going from A to B were forming an SU cut, right? So deleting those edges, if we delete those edges, then there is no path between A side to B side. So there is no path from S to U. But in the same vein, we can also claim that if all the edges lying on this side, if all the edges lying across here, which go from A side to B side are deleted, then what actually happens is there is no path from S to U remaining. But similarly, there is no path from T to U remaining either, right? Because when these edges are deleted, then there will be no path from T to U also, because no edge goes from this side to this side if we delete all these edges. So this set of edges also forms a TU cut, even though it may not be TU minimum cut. It may not be the minimum cut, but at least it is a TU cut. Like if we take T on source side and U on sink side, then this forms a TU cut. But note that the size of this cut is given to us as less than K. Like we took the SU minimum cut size as less than K, and we are talking about this cut. So this cut has size less than K. So this means that this is an SU cut of size less than K, but this is also a TU cut of size less than K. So this forms a TU cut of size less than K. But note that it is not possible because we were given that size of TU minimum cut is equal to K. So if there exists a TU cut of size less than K, then the minimum cut cannot be of size K, right? Suppose minimum cut is of size 5, but we have obtained a cut of size 4, then that is a contradiction. So are you able to follow, Dhruvika, what I'm trying to say here? That we are given that size of TU minimum cut is K, but if T lies on source side, then this cut also forms a TU cut. And this forms a cut of size less than K. And it is not possible because minimum cut was of size K. So, so is this sort of argument clear? Similar argument can be given for the other side also. Suppose T was not in this side, but it was on the sink side. Then we can say that this cut is an SU cut. So there is no path going from S to U, right? So, but there can be so in the same vein, if we delete this set of edges, then there will be no path going from S to T either. So there will be no path going from S to T either, because deleting these sets of edges, no edge goes across A to B. So there is no edge from S to U, no path from S to U. So there will be no path from S to T either. So this forms an ST cut also. And if T lies on this side, then this forms an ST cut. And we are also given that ST minimum cut is also of size K. But what we obtain here is a cut of size less than K, because we initially assume that SU minimum cut is of size less than K. So maybe you can think about it yourself also while I sort of write it down. Uh, Let this cut be A comma B, where S lies in A and U lies in It's a very cute question. I kind of like it a lot. That's why. So yeah, and U lies in B. Suppose size of this cut is equal to K prime such that K prime is less than K. And why is K prime less than K? Because size of SU minimum cut is less than K. So maybe yeah. So what this actually means is that now vertex T lies either in A or in B because A and B form a bipartition of the vertex set, right? Right. So if T lies in A, then A comma B is also a TU cut. If T lies in A side, then it is a TU cut. Is also a TU cut of size K prime. But TU min cut is of size K. And so we should not get a TU cut of size less than K. But we have already obtained a TU cut of size less than K because K prime is less than K. Hence, this is a contradiction. Similarly, if T lies in B, then A comma B becomes an ST cut, is also an ST cut of size K prime, which is again a contradiction as ST min cut is a size K. Hence, what we actually obtain is in both. So we take two cases, and in both cases we obtain contradiction. So actually, there's a contradiction in all cases. So what we have actually shown is that size of SU min cut is always greater than equal to K. So something like this. So, so I hope this sort of argument is clear to you, Dhruvika. We have a couple of minutes left. It's 7:57 right now. So if it is not, maybe you can ask in chat. I'll try to uh, explain it a bit more in the remaining 2 minutes which we have. Or like, okay, so Dhruvika says she understood. So nice. So I guess so these were the questions which I had for today. So I guess we can wrap up then. So while uploading this document, I'll also put these diagrams into this document. So any other doubts or comments which you have regarding anything, Dhruvika? So okay, so Dhruvika has some doubt. So what did you want to ask, Dhruvika? So if you have some doubts, like you can ask in chat, and I'll try to answer it in the remaining time. So what did you want to ask, Dhruvika? Okay, so will there be all MCQ based questions in final paper? So actually, Dhruvika, I don't know that about the I don't know that much about the course logistics because I'm just a problem solving TA. So maybe you can ask this in the NPTEL discussion forum. So in the discussion forum, I believe you will get an answer to this. Like, will there all be MCQ based or will there be other problems also? Like, so I hope you know that there is a discussion forum for this course also on the NPTEL side. Like, you can easily search for it. And okay, no, I am not in the Discord server also. So no, Druvika, I'm not in the Discord server of this course. In fact, I know for the first time now that the Discord server exists. Maybe you can ask in the Discord server also, and you will obtain the answer to this query. Like, I don't know much about logistics of the course. I just know about the problem solving sessions and all. Okay, so I hope you have no further questions. Like if you have, maybe I can take it up next time also because I believe we are running out of time for this session. So once again, I guess thanks for joining, Dhruvika, and thanks to everyone who is watching on YouTube also. So hopefully we'll see you guys next week also, same timing, Tuesday 6 to 8 p.m. So yeah, hopefully we'll see you guys there. So maybe I'll close the recording for today, and yeah, you can also leave the session, Dhruvika. Thanks for joining, and bye bye.